Hello, and welcome to the Farrat Construction CPD Module 1, an introduction to thermal bridging and structural thermal breaks. This CPD is worth 20 credits. Let's get started. On today's agenda, we'll be looking at why we use thermal breaks, typical applications, the structural thermal break options, a deep dive into energy loss and condensation, and some of the thermal and structural design considerations. Modern building design and regulation recognise the importance of energy conservation and occupier comfort in all aspects of construction detailing. Developments in material science and advanced manufacturing techniques have tracked these requirements, and alongside designers' desire to push the boundaries of detailing and aesthetics, have kept a palette of flexible options available for use in every building scenario. One of these ever-developing options is the use of structural thermal breaks. Structural thermal breaks are a solution to avoid thermal bridges in building details that pass between spaces of differential temperature, specifically where the thermal break material needs to perform both in transmitting structural loads as well as preventing thermal movement across the connection. The two primary reasons for avoiding thermal bridges are to reduce energy loss and to mitigate against the risk of condensation. The impact of poor detailing resulting in thermal bridges in the building envelope is well documented. The resultant energy loss can impact severely on the overall performance of a building in respect of the amount of energy required to heat or cool a space and the cost of that energy, both monetarily and environmentally. Building regulations typically guide the designer in understanding the minimum requirements in thermal performance of building elements to achieve satisfactory thermal performance in respect of energy loss or gain. In England and Wales, approved Document L gives detailed guidelines for calculating the target emission rates and target fabric energy efficiency rates and the minimum values to satisfy both of these requirements. Alongside energy loss, thermal bridges in a building fabric can result in condensation and mold growth. This is where the temperature of a room's internal surfaces is sufficiently low for moisture-laden air to reach a dew point, and this condensates, and in some cases for the propagation of the mold spores to occur. Looking at more detail in the type of buildings this can occur, we can see that structural thermal breaks can be incorporated into any detail where there is a calculated or perceived risk of thermal bridging. This is typically in details that occur in building envelopes or where significant temperature difference is likely to occur between compartments, such as highly controlled atmospheric environments, plant or server rooms, or warm, high humidity environments, such as breweries or swimming pools. So, what options do we have? Well, there are two principal types of structural thermal breaks, mechanical and solid-state plates. Mechanical thermal breaks include combinations of structural components and compressive insulating materials, which are used to compensate for the poor thermal performance of the continuous steel elements. The alternate type, solid-state thermal break plates, are used in conventional connections as structural spacers that also have a high thermal performance. In respect of energy loss, all materials have a thermal conductivity value. The majority of materials with high structural properties have poor thermal conductivity, so these materials have to be supplemented or isolated with better performing materials in order to achieve an overall satisfactory thermal performance. In order to assess the relative thermal performance of combinations of materials and details, empirical calculations are carried out using the respective conductivity values and figures for the climatic environments into which they are due to be installed. The simplest of these calculations is for plane elements, which are expressed as a U value. More complex to calculate are linear details, which are expressed as a psi value, and most complex to calculate are localized elements or point connections, expressed as a chi value. This last value is only able to be attained from complex three-dimensional modelling and is typically where the need for structural thermal breaks is required. Once the thermal transmittance through a detail is established, this can then be used to evaluate likely performance in relation to a critical temperature factor. These factors relate to a range of building types and the propensity for moisture to be present in the internal spaces. The higher the likelihood of there being moist air present, the higher the likelihood of moisture condensing out and causing problems. As such, the higher the risk of condensation, the more important it is to have sound thermal performance of the building fabric to avoid associated problems, such as mold growth or corrosion, both internally and within the building structure itself. A critical design consideration here is thermal performance. Finite element analysis is still currently the only way to empirically establish the performance of an elemental point connection. However, this is a time-consuming and complicated process which consequentially is infrequently used to assess details. Finite element analysis thermal modeling not only takes into account the direct connection of materials, but also the significant elements surrounding the connection. These surrounding elements have such an impact on the final result that they cannot be ignored in a simple calculation. In the absence of a full thermal model of the actual detail being used, typical details can be modelled and used as indicators of likely performance to specify materials that will meet the design requirements. The Building Research Establishment, otherwise known as BRE, has produced indicative details available online to assist in the specification of solid-state thermal breaks, which can be relied upon in the absence of a full 3D modal analysis. After determining the thermal performance of the construction detail, either through FEA modelling or using the exemplar details for the smallest cross-sectional area of penetration or connection, you should then select the thickest thermal break plate with the lowest thermal conductivity to ensure the connection achieves the optimum performance. Another critical design consideration is the structural performance. When designing structural connections with solid-state structural thermal breaks, the following additional checks should be undertaken to ensure correct performance. Here is a checklist for thermal breaks that require a HSFG bolt, predominantly a requirement in the US or the UAE following US design principles, but becoming more relevant in buildings with external skeleton structures. As with all construction components, correct handling and installation are a critical part of the performance. Solid-state structural thermal breaks are a relatively simple building material. However, attention should be paid to any specific manufacturer's requirements for handling, and this should also include connection-specific labeling, material conformity certification, and batch traceability to ensure avoidance of site and design validation issues. Structural thermal breaks can be designed into any simple or moment connection. In steel connections, the introduction of the thermal break typically will not impact connection and member size, but will allow flexibility in achieving uncompromised details. As well as the simple evaluation of a compressive strength figure, account should also be taken of the material's ability to disperse loads from highly loaded points of a connection. This factor and the selected material's ability to deal with these loads should be addressed by the material manufacturer. All material-material connections have the potential to rotate under load. Note should always be taken of a chosen structural thermal break to resist these loads and not to compromise the short and long performance of a connection with undue flexibility or excess creep. Structural thermal breaks typically limit the extent of their load transmittance for design purposes to the transferal of compression loads. The main connection elements typically deal with shear loads, and notice should be taken of the effective connection's length in relation to the thickness of the structural thermal break specified. 25 mm thickness would typically be the optimum without having to consider increasing the size of the bolt. Extensive independent work has been carried out throughout the world on the performance of structures in fire, and conclusions reached with regard to steel and concrete. This figure shows the simplified global presentation of physics schematical processes in Portland cement concrete during heating. Rules for fire protection are formulated in relation to time, and the safety afforded to persons exiting the building and firefighters attending the blaze. A large part of this is the propensity of materials used to either contribute to the fire load and ease of ignition or continue to burn, causing the fire to spread. Structural thermal breaks, like most building materials, can be produced with different grades of flammability and performance under fire loading. Where fire sits high up on the order of risk, alongside structural thermal performance, choose a certified fire-resistant material. This is a topic that we'll look at in Module 2 of Structural Thermal Breaks. Congratulations! You have now reached the end of this introductory module. For more information on this subject, or to discuss an engineering challenge, please do contact us. Remember that reputable manufacturers like Farrat will always be able to discuss design proposals and assist in specifying the right product for the job.